So let's come away from like these nitty-gritty calculations and try to think about some slightly more conceptual questions you might have at this point of view, at this time. So, okay, I gave you like, I don't know, 6 instructions or something, like toggle and if A, then toggle B. There's these classical reversible instructions, a few of them. And then it's like, you can also have Hadamard, which has this little, definition with square root halves and pluses and minuses. And it's like, oh, you can also have this weird clockwise I invented that, has this definition. And then I was like, okay, that's it. These are your basic instructions. But of course, from these, you can code lots of new things. You can code new subroutines or new manipulations or these new composite instructions. And each of them has its own, definition, its matrix or its paths diagram. So one question you could ask is like, what are all the possible operations you can get? Or like, what is the nature of like all these composite instructions that you can build up? So let's say question 1. Like, what are all the possible instructions? Okay, that's kind of a bit philosophical or high level. A more concrete question you might have is, apparently, whenever you do some quantum operations, the law of quantum mechanics says you'll get to a state where the sum of the squares of the amplitudes is 1. And indeed, that did happen every time. But, at this point, you're probably like, this is like, why did this happen? This was like a miracle. We did all these like weird instructions on numbers, and like somehow like this happened. Like, why did that happen? To put it another way, like our quantum operations seem to have the following magical property. Which is mathematically called the Unitary property. Which is, given a valid state, and by valid I mean one that obeys the laws of quantum mechanics, so like squared amplitudes sum to 1. If you apply the operation, the new quantum state, or the new state, is also valid in the same sense. So it preserves the sum of the squares of the amplitudes. And why is it called unitary property? It's like mathematicians invented this term, but it's because like, you have 1 unit of squared amplitude coming in, and this magical property is that like you do the operation and you still have like 1 unit of squared amplitude coming out. So it always keeps you at 1 unit of squared amplitude. So why does this keep happening? I mean, it's good that it happens, and it evidently kind of has to happen if the laws of quantum mechanics are true. But why? And answering this question why will also help us answer question 1. Well, I guess maybe I'll sort of tell you now, maybe the last law of quantum mechanics that you need to know in this course, which is about the nature of what quantum transformations are possible physically. So this is like a law of quantum transformations. Goes together with our law of quantum mechanics about like, every valid state has to have squared amplitudes summing to 1. And maybe the law of quantum measurement that tells you how the probabilities with which you see different measurement outcomes. So let me write this. So suppose k qubit, k is like 1 or 2 or 3 or anything really, but a k qubit manipulation subroutine or operation has a 2 to the k by 2 to the k matrix, or equivalently paths diagram. I mean, you write down all the amplitudes for how it transforms all the 2 to the k different basic states. And furthermore, suppose this happens to have the unitary property. So you might have a hard time understanding whether a given transformation has this unitary property, that it always preserves the squared amplitude summing to 1. But let's just say that you understand that it does have this unitary property. Then this transformation is physically possible. Well, at least in principle, I'll say. But, just it's physically possible. And conversely, by which I mean, these are all the physically possible transformations. Okay, so this is sort of telling us a law of nature that the physicists worked out. Like, if you want to know, how the state of anything, the state of some particles can change, well, it can precisely change by, a paths matrix operation, a paths diagram operation that has this unitary property. And some parts of it, are obvious in the sense that, we already told you there's a law of quantum mechanics that the state of some particles always has to have squared amplitudes summing to 1. And therefore, apparently, if you do a physical transformation, it must keep the sum of the squares of the amplitudes being 1. But the other half of this is saying is the converse, which is that if you describe a matrix which has this property that always keeps the sum of the squares of the amplitudes 1, then this is a transformation that can occur in our physical universe. Now, just like lots of things, there's nothing in the law of nature. There's no law of nature that prevents us from having flying cars on Mars. That's consistent with the laws of physics. It doesn't mean it's easy to accomplish this, but there's nothing in the laws of physics that says the laws of physics said you could have some flying cars on Mars. That's fine. It could be very hard to arrange for it, but it's possible. And similarly, for some 1,000 qubit manipulation instructions defined by 2 to the power 1,000 by 2 to the 1,000 matrix that has the unitary property, it could be very difficult to cause this transformation to occur in nature, but in theory, it's possible. Okay. So maybe one thing we should check or reflect upon is I just told you at the beginning of the course, toggle A, that's a valid quantum transformation. And Hadamard A, that's a valid transformation. And if A and B, then toggle C, that's a valid quantum transformation. So maybe we should go back and check that these all have the unitary property. And we'll also see that they have the unitary property. And that's good once we check that our basic instructions, well, I shouldn't say basic, I don't know, our given instructions, pseudocode instructions, have the unitary property. One thing that's good about this is that it just follows that any subroutine you can build up from them also has the unitary property. Because if each of your little instructions never changes the fact that the squared amplitudes sum to 1, then you do 10 of them in a row, then you never change the sum of the squares of the amplitudes. It stays 1. And therefore, the composite instruction also doesn't change the sum of squares of the amplitudes from 1. The composite instruction also has the unitary property. Okay, so by checking that our little basic pseudocode instructions have unitary property, we check that at least everything that we can program using these instructions is also unitary and therefore is physically possible. We kind of know, similarly, like if each of these little instructions corresponds to a physically doable thing, then you can just do them all in a row according to the code, and that's also physically doable. But, let's check it. Actually, let me say one more thing before we check that. Once we check that, what we'll have seen is that any code that we can build up from our primitive pseudocode instructions has the unitary property and is therefore physically possible. But you might ask about the converse of that, which is like apparently anything with the unitary property is physically possible. So does that mean anything with the unitary property we can code up using these primitive instructions? And whether or not that's true actually depends on which pseudocode instructions I gave you. If I was like, the only code you get is toggle, you'd be like, I don't expect to build up all possibilities. There's no way I can build up Hadamard if all you give me is toggle. So I'm like, OK, I'll also give you Hadamard, and so forth. That question is like harder to answer. I'll just tell you the answer, which is that it's fine, don't worry about it. But this requires like some mathematical theorems that we're not going to get into. But I'll summarize it in words. It's a theorem that, OK, I'll tell you a theorem that's not quite true, but I'll revise it. Something that's not quite true is the following reassuring fact. Every qubit manipulation operation that has the unitary property can be programmed using those 7 instructions, like if, then, toggle, toggle, and Hadamard, and the ones that I've given you. That's almost but not quite true. What's literally true is that like for any transformation with the unitary property, you can program it to arbitrarily good accuracy. You can't maybe literally exactly get it, but like you can get maybe a slightly different matrix where every amplitude is correct within 1%, or 10%, or like 0.1%, or 0.001%. Any tolerance you want, you can program it. So it's a bit of a math thing. You can't maybe literally program every single one, but you can get arbitrarily close to any single one. The takeaway message, therefore, being, don't worry that I didn't give you enough pseudocode instructions. We've proven that like these 7 instructions or whatever are sufficient to program anything you want, up to arbitrary accuracy. And also, there's one more twist. I didn't give you any instructions that let you make complex amplitudes, because let's keep it simple. But here you should also allow complex amplitudes. But again, you can take my word for it that anything you can do in quantum computing with complex numbers, you can do without complex numbers. Or if you really want to get those complex numbers, you can give yourself like one little new instruction called phase, which has like this matrix, 1, 0, 0, I. And then if you have this one, then you can really get everything with complex numbers. OK, but this was just to maybe try to reassure you that like the pseudocode instructions that we have are going to be sufficient for doing everything. And now let's try to check that, OK, these at least have this unitary property. So probably we'll get halfway through this check, which is fine. So let's start with this question. Why are the classical reversible instructions unitary? Remember, I divided all the qubit manipulation instructions into 2 categories earlier. The classical reversible ones, the ones with the ifs and the ands and the toggles and so forth. And then maybe the superposition creating ones like Hadamard, and I suppose this clockwise as well. And we'll do this check again in 2 parts. So this one is actually not hard to see. It's particularly, there's an intuition behind this. So what's up with classical reversible instructions? Well, remember, their paths diagram. They're defined by their paths diagrams. And they look kind of simple. So let's say you have a classical reversible instruction that operates on 2 qubits, like if A then toggle B, or swap A, B. Then its paths diagram, okay, it has this on the top, and it has this on the bottom, all the possibilities for basic states on the bottom. And because it's like kind of classical, it means that like, you know, if you start in a basic state, you just, with all amplitude, go to some other basic state. So we just have like arrows, and like all of them are implicitly labeled by 1. That's the classical part. What about the reversible part? The reversible part means, well, you cannot have like this. This will never occur in a classical reversible instruction, because like this is not reversible. It does not have an undo, because like it couldn't have an undo, because like if it had an undo, where would the undo send 1, 0? You're like, I don't know. Like I might have come from 0, 1, or I might have come from 1, 0. I don't know how to undo this. So in order to be reversible, you see that everything in the output has to have in degree 1. Right? It has to come from like a unique, I don't know, it has to come from a unique basic state. Okay, so if you don't have in degree 1, you can't be reversible. And on the other hand, if everybody has in degree 1, then it's perfectly reversible. Really, I'm just saying like this is a directed matching. It's like a permutation. So all the classical reversible instructions have paths diagrams that look like this. And from this fact, like once you know this, it's kind of clear why these things have the unitary property. Actually, maybe I'll ask you if you can suggest why that's true. Yeah? Yes, exactly how I would put it. The incoming, so why are these unitary? So, yeah, so like if the incoming state is, as was suggested, like, you know, A amplitude on 0, 0, B amplitude on 0, 1, C amplitude on 1, 0, and D amplitude on 1, 1, with A squared plus B squared plus C squared plus D squared equals 1. So it's like saying, if you're given a valid state where the squared amplitudes add up to 1, well, then the, you know, Three Stooges noises here, like outgoing state, you know, you'll have, in this case, if you have A amplitude on 0, 0, then you get A amplitude on 0, 1. And then if you have B here, you have B amplitude here, and so forth. You would just get them permuted around. So you'll have, like, still has amplitudes A, B, C, and D just permuted. And therefore, the squared amplitudes still sum to 1. In fact, hypothetically, if the squared amplitudes were allowed to sum to something other than 1, then if you did classical reversible operation and just blindly following the rules, the sum of the squares of the amplitudes would be the same thing it was before. So, you know, mathematically, doing this classical reversible operations does not change the sum of the squares of the amplitudes. In particular, if it starts at 1, then it stays 1. Okay, so these ones are unitary, and this kind of really relied on these operations being reversible. That was like kind of key to it. So that's clear. Next time we'll see why, for example, Hadamard operation also has the unitary property. And it's not really so much there's an intuition. It's just you got to check that Hadamard luckily has this property. And that's why we focus on Hadamard. It's like one of the few lucky operations that has this unitary property. So we're like, great, we'll take it. Yeah, so next time we'll see why that happens.